So let me start by saying that we're tying up loose ends. Yesterday we did a whole bunch of stuff with the differential equations, and I want to clarify that I have certain expectations for that. And look, I know we have loose ends here, and these loose ends come from us not being able to get all the momentum stuff in. We focused on one thing. We focused on collisions. So just as a quick recap, I hope you remember our discussion about collisions. In most collision questions, we're talking about a portion of what might happen in a system. So we might have a situation where, what the heck is going on with me? A situation where we have two objects that are going to experience a collision. If you remember from first semester, we did problems like this, but most of the problems, the collision was somehow embedded in what was happening elsewhere in the problem, in that the collision part was just the instant before the objects came into contact and the instant after they were in contact. But usually there was a larger narrative around what the collision was doing. Does that ring a bell? So in this collision, I have two objects, and we know that there's a variety of ways in which the collision can occur. We broke them down into two categories and actually kind of introduced a third, kind of. The first category were inelastic collisions, which makes up the basis for most collisions that occur in nature. We remember that momentum is a measure of an object's inertia while moving. It's a vector quantity. And in an inelastic collision, the total momentum before has to equal the total momentum after. And this is true for all interactions unless there's an external force on the system. Now, we'll see situations in which external forces act on systems, but we still say that the momentum is conserved. And that's because we focus. We're focused on the moment before and the moment after. As long as their interaction is very fast, external forces don't generally cause much of an effect. It's only in situations where the objects are in contact for an extended period of time will an external force actually play a role in the collision. And that seldom happens in the problems we have. Collisions are typified by them happening fast. Now, we remember, I hope, that the kinetic energy is not the same in an inelastic collision. That in inelastic collisions, some of the energy is going to be transformed into something else. Now, there is a subcategory of inelastic collisions called perfectly inelastic collisions. And in those, they were different in only the fact that the objects joined together during the course of the collision and moved with the same velocity. One train car coupled to another train car, a fullback tackled a running back, something like that. A bird ate a fly. These are situations in which you could say they are a collision, but the objects have the same velocity after the collision. So we tend to join their masses together and treat them as if they have a single velocity. Now there's another category, elastic collisions. And elastic collisions happen in basically one or two ways. True elastic collisions happen very seldom in nature. Subatomic particles have elastic collisions, but that's because they don't even make contact with each other. The electric force pushes them apart before they ever can make contact. But we have some kind of physics problems that have been contrived to talk about the possibility of an inelastic collision by storing the energy someplace else while they're in contact. We did two problems like that, right? A problem where a brick kind of slid up on top of another brick, or one where the energy was stored inside a spring. We could treat those like inelastic collisions too. They are predicated on the idea that not only is the momentum conserved, but the kinetic energy is also conserved before and after the collision. And we call those elastic collisions. Now, to ensure that we are all remembering this the same way, would you take a moment and tell me the result of the collision that's here if I were to tell you it is a perfectly inelastic collision? So I want you to have a little flesh in the game today. I'll give you about 60 seconds. What is the result of this collision? What is the magnitude and direction of the velocity after the collision? Of what to do is on here. And we went through it. So you should have got, 1/5 meter per second. I know some of you didn't and have an answer that's not that. Some of you didn't finish. You're going to have to be faster than that. Calculating momentum is just MV. So I've got to make a decision about what direction I will call positive, because momentum is a vector quantity. So those bars should have alerted you to that fact. So I start with 8 times 4 plus 12 times -3. This is the momentum of the system. I sum up the momentum of every object in the system. But I say that they have a collision in which it is perfectly inelastic, so I am telling you that they will have a combined velocity for their total mass of 20 kilograms. So when I work that out, my velocity is going to be 1/5 meter per second to the left. Now, I need to pause here. If you just wrote -1/5 meter per second, that's not going to be okay this semester. I asked specifically for you to tell me the magnitude and direction of the velocity. And if you just left it as negative, no amount of drawing an arrow is going to change the fact that they want you to interpret the meaning of the negative answer. You have to be the one to say it's in the negative direction. And left is a way to do that. So just leaving the negative sign out there is no longer sufficient. In fact, it is not uncommon for them to have a picture, and next to the picture, have something like this. They are telling you something, and you need to use it. If there's a picture like this anywhere on the diagram, they are telling you the positive direction that you have to use for the course of the problem. So if you see this on there, and I will be putting these on problems, I'll be cutting and pasting these off of old AP exams. I will be making sure if I see it on an AP exam, I use it, because your answer is left or the negative X direction. If they have a indicated direction, that is positive. But leaving the negative sign here, that's not enough any longer. Does everybody understand? Please make sure you have that in your notes for our next work on this. I don't want to spend a lot more time on collisions. I'm going to put a couple collision practice questions in the homework that I'm assigning, but the homework I'm assigning is on our next unit. There's not going to really be much here. I want to do a quick reminder too about the concept of impulse. I'm going to work this in a little bit over time because there are other forms of impulse. But we did define it before the break. We just didn't have any practice for it. Impulse is defined as change in momentum. It's defined as change in momentum. And it is a vector quantity, but unfortunately, the symbol for impulse is uppercase J. I never write uppercase J. I write the word impulse. Just like work, remember how I used to write the word workout? I'll do the same for impulse. The uppercase W is too close to what we use for weight. And uppercase J just doesn't jive with me for impulse. Although on your equation sheet, that's what they do. Now, there's a couple things about this that I think are important for you to understand. And this is review, I think. But this is the effect side. You can visually see this. You can see the object's momentum change. You can measure it. It's specifically the final state minus the initial state. I don't care what happened in the middle to cause it. The impulse is just the final minus the initial. But be careful. The direction of impulse is in the fact that it's a change in momentum. For example, imagine I have an object traveling to the right, and something happens, and suddenly it's still traveling to the right, but slower. This would be its final momentum. This would be its initial momentum. What is the direction of the impulse? To the right or to the left? There is a clear change in velocity. What you need to ask yourself, and this is worth writing down, so you don't have to worry about your intuition, you have it down. The direction of impulse is in the direction that a force would be required to make the change in momentum. The direction of impulse is in the direction of the force required to make the change in momentum. Now, this is the part that's rough. Do I have to say that again? All right. The part that's rough is that force doesn't have to be constant. That force could have had multiple directions. But impulse only takes into account the before and after when it comes to its effect. So the direction of the impulse will be in the direction that a single force would have been used to cause that change. The reason I have to say that is, this one is easy, it's to the left. But what if after we're done, the direction is like this way? Well, there could have been more than one force that caused this over the duration of the impulse. Like there could have been a force this way to stop it from going to the right, and another force this way to cause it to go somewhat downwards, but the impulse would then be this way. Right? The combination of those two forces again, still bits of review. Here's where we'll get some new stuff, though. First semester, I did talk about this, but now let's make it plain. The cause of an impulse is a force for a period of time. But this would be how I would describe it in AP Physics 1, and we would deal with constant forces. But this is AP Physics C, so a more robust way to do this is to recognize that the force doesn't have to be constant. And therefore, an integral could be used to calculate the impulse if you have a time-varying force. Now, to calculate this impulse, don't be tricked too much. They can give you a complicated expression for force. Well, something that has something to do with time. But don't be too worried about it. If you know the before and after, you don't have to integrate. There's very few problems where they ask us to integrate the force as a function of time. There's plenty of problems where you're asked to calculate the work by doing integration, but not as many for impulse. Generally, impulses occur over very short periods of time, and we don't have very many natural time-varying functions that would work here. A rocket engine would, and for a rocket engine you would have to do this because they often have a time-varying force. But there's just not that many, and they don't ask it very much on the AP exam. What they do, however, do is they do require you to understand that if it is an integral, there is another way to figure out impulse for a time-varying force. Let me give you an example. This is something we're going to do in the lab next week. In the lab next week, as a consequence of one car striking the other could be described as a graph. In fact, this is what the lab will be about. So consider what that graph would likely look like. Let's start with what the yellow car saw. And let's say that from your vantage point in the classroom, the left side of the classroom is positive. That all good? Is that all good that way being positive? Because I have to write it all backwards for where I am. So that would mean that the yellow car, for a long time, experienced no force. And then for a short time, experienced a positive force, and then experienced no force. Do you guys agree with that statement? Oh, wait. No, I'm right. Yeah, for a long time, the yellow car is experiencing nothing. It's just sitting there, right? And then the green car hits it. During the time that the green car and the yellow car are in contact, there is a force on the yellow car that way. Make sense? So, clear? All right, green car. For a long time, the green car experiences no force. It's moving, but it's not experiencing a force until it encounters the yellow car, which pushes on it this way. That has to be negative. They separate, experience no force. Okay, good so far? You could be asked to determine the impulse experienced by the yellow car. Yes, sir?
They're experiencing the exact same force, right?
Well, they would have to be, right? Newton's third law would require it because there are two objects in contact, and therefore they'd have to follow that rule. And this time interval would also have to be the same because it's not like one could be touching the other without the other one touching the first, right? So the force and the time have to be the same due to Newton's third law. And that's part of what we want to prove, that we can figure out the impulse from the graph, which is one thing I will ask you to do. This is technically integration. The force is not constant over the interval. So you wouldn't be able to use force times time because the force is increasing while the spring is being compressed and then decreasing as the spring is being extended. But you could find the area under the curve, which is what you're doing when you take the integral. All you wonderful AB kids are just learning that now, right? We covered that. You're still doing the trapezoids. Are you done with trapezoids? Awesome. What are you doing now? Here we go. The area under the curve has to be the impulse. And more importantly, it has to be the change in momentum of the car. Consequently, this area also has to be the impulse. And that also has to be the change in momentum of the car. Clearly, one of these is positive and one of these is negative. We would suspect, under these circumstances, that the total momentum change of the system is zero, right? These should be equal and opposite. And in a collision, the momentum change of the system is zero. The momentum stays the same in a collision. We'll prove it in a lab doing this. But here is where you need to understand what is meant by being able to take the integral. It's the area under the curve. This is the most likely use of that knowledge on the AP exam, but this is actually brought up a bunch of times. Worth knowing. And they actually might produce a graph that looks like this. You shade it in and you solve for the area. It's that straightforward. I don't want to do a bunch of that now, but I'm including one of these as one of your practice questions on your homework. That's, believe it or not, that plus what we talked about first semester is really all I want to talk about when it comes to impulse. You'll need practice, and I'll provide practice. But, yes, sir? Okay. Where I really want to talk about is something that was missing first semester, and this is where we really need to spend some time on what's known as center of mass. How many of you have heard of center of mass before? Should be 100% of you. 2 questions on your semester exam. Sorry. That's my fault. Just ran out of time. So, and to be honest, I keep forgetting that it's in this unit because it used to be in the next unit. So I'll take the fall for that one. But who's heard of center of gravity? All right. They are not the same. An object has a center of mass even if it's not experiencing gravity. But it can only have a center of gravity when experiencing gravity. So I want you to understand that for an object experiencing gravity, gravity acts as if it's focused on the center of mass. That will be important. So I'll say it again. For an object experiencing gravity, gravity acts as though it's concentrated on the center of mass. Imagine you want to tip a box over. Now, anybody ever tipped a box over? You should probably be aware that you might have said the phrase, it's a little top heavy. Have you heard that before? That is referring to the center of mass. It is easier to tip something over that is top heavy than something that is not. Because, and this is not super important, but all you have to do is get the center of mass over the pivot point, known as the fulcrum. If you can get the center of mass over the pivot point, gravity will pull it over the rest of the way. So if the center of mass is here, this object will continue to fall over. I just have to get it tipped over enough so that gravity will do the rest of the work. And gravity's acting downwards here. It's on the other side of the pivot point. But if you have a low center of gravity, a low center of mass, it's much harder to tip something like this over. Thus, football players get low when they're about to hit somebody to lower their center of gravity. All right.